This video presentation is to introduce and discuss the big name value theorems of calculus. These include the extreme value theorem, the intermediate value theorem, the mean value theorem, and a few other named theorems that are related. Fermat's theorem for extreme points and Rolle's theorem. In mathematics, a theorem is a statement that summarizes conditions that will guarantee a particular property is going to be true. The collection of all of the conditions that need to be satisfied in order for the property to be true is called the hypothesis. The property that is true, or the statement that is guaranteed by those conditions, is called the conclusion. In order to understand these theorems, you need to be sure that you know the names, the hypotheses, and the conclusions of each theorem. In addition, you need to know when you would use a theorem and what steps you would need to take in order to apply the theorem. The common theme throughout all of these theorems is that continuity plays an essential role in all of the hypotheses for the theorems. So let's review some of the basic ideas of continuity. First, we start with the idea of continuity at a point. So I'm going to draw a graph of a function. Here's my function. I've introduced a particular symbol, curly z, that represents the point where we're interested. The idea of continuity at a point is that the limit exists at the point, and the value of the function exists at a point, and the limit and the value of the function are the same. In my example, my function does not exist, and so my function is not continuous at z. If I were to add a point, now my function's defined, but my limit's not defined. If I look at the limit on the left and the limit on the right, they go to different values. On the left, I go to this point. On the right, I go to the lower point. And so again, this time my limit doesn't exist. My function is not continuous. On the other hand, if I added a point to match one of the limits, so let's do the top one. Now I have a limit on the left, and the value of the function matches the limit on the left. I would say that my function is left continuous. On the other hand, if I were to have defined my point so that the bottom limit was matched, now the limit on the right exists and agrees with the function, and so I would say I am right continuous. If I thought about any other point other than where this function breaks, I have a continuous function. For example, if I thought about this point to the left of where we were originally, I have limits going to the point, and since the point is exactly the same as the value of the function, I'm continuous at that point. The hypotheses for our theorems related to continuity focus on the idea of being continuous on intervals. Here's a new function. My function is continuous in many places, but it's also discontinuous at 4 different points, at -4, -1, 1, and 2. The idea of continuity on an interval is that I'm continuous at every point in the interval. As I look at my function, assuming that my function goes on forever here on the left, at every point in this interval, my function is continuous except at -4, because my limit doesn't match the value of the point. I would say my function is continuous on the interval -infinity to -4, not including -4. There's another interval from -4 to -1. Notice this time my function is continuous at -4 as an endpoint, because the limit going towards that end for the interval agrees with the function. On the other hand, my function is not continuous at -1 because the function doesn't exist. So I would say my function is continuous on the interval -4 to -1, including -4, but not including -1. At every point between -1 and 1, my function is continuous, but not at either endpoint. On the left, it's because my function doesn't exist. On the right, It's because my function is going to a vertical asymptote. There is no limit. So I say my function is continuous on -1 to 1, that entire interval. Similarly, my function is continuous on the interval from 1 to 2. Not at 2 because the limit doesn't agree with the value of the function, and not at 1 because again the function has a vertical asymptote. Finally, if I think about the end, from 2 on, again assuming that this function goes forever, my function is continuous from 2 to infinity, but not at 2. The intervals that we've listed are the largest possible intervals we can create for which the function is continuous. However, I could look at smaller subintervals. So for example, between -4 and -1, I could go from -3 to -2. And notice now, my function is continuous at both endpoints. I would write that my function is continuous on the interval -3 to -2. In addition to continuity, differentiability plays an important role in several of the theorems. Let's review the basic idea of differentiability. A function is differentiable means it's both continuous and smooth so that we can define a tangent line at a point. Here's an example of a graph of a function that will allow us to explore some of the possibilities. At -1, my function is differentiable. I have a clear tangent line at that point. On the other hand, at 1, I do not have a clear tangent line. I might think about having a line coming from the left. This means I'm going to be left differentiable. There is a derivative coming from the left, but there's also a derivative coming from the right. The problem is those two don't agree, so my function is not differentiable at that point. The third point that's interesting is at x equals 3. Here, my function is not even continuous, and there is no derivative at this point. I can't draw a tangent line for an isolated point. It has to be connected to the function. So my function is differentiable at -1, but f is non-differentiable at both 1 and 3. The idea of being differentiable on an interval is similar to the idea of being continuous on an interval. It means I need to have a derivative at every point in the interval, and at endpoints I would need to be differentiable from that side. For the function that I've illustrated above, to the left, my function is going to be differentiable on the interval -infinity to 1. Now at 1, because the left derivative exists at 1, in other words, coming from the left side, my function has a derivative, I can say that my function is differentiable on the interval up to and including 1. My function is also differentiable between 1 and 3. Every point between 1 and 3, I have a derivative. I never have a derivative at 3, but I do have a right derivative at x equals 1. And so I can say my function is differentiable on the interval starting at 1, including 1, up to 3. But it would be incorrect to say I go from -infinity to 3 because at x equals 1 I don't have a derivative from both sides. Other intervals of differentiability include the interval 3 to infinity. Similar to continuity, I can also do intervals that are included. So for example, I could say my function is differentiable from -2 to 0. This is because on the interval from -2 to 0, my function has derivatives. I could also include the endpoints, because on that interval, I am differentiable up to and including the endpoints. We're now ready to introduce our value theorems. The first value theorem that we want to focus on is the intermediate value theorem. The key to remember is that the word intermediate means in between. The conclusion of the theorem is what is guaranteed by the hypotheses. So as we look at the conclusion, we want to focus on what is the essential idea we're trying to show. The goal of the intermediate value theorem is to show that the function has a value at some point. The hypotheses give us an idea of what type of point we're looking for. The key is we're looking for a point that has a y value of L that's somewhere in between the value of the function at the endpoints. To illustrate this theorem, I've graphed a function with an interval from a to b. Notice that my function that I've drawn is continuous on that interval. That's one of the hypotheses. My function is continuous on the interval from a to b. Secondly, we need to understand what the value of the function at a is and what the value of the function at b is. The intermediate value theorem says once you know a function is continuous on a closed interval, notice I have to include the endpoints a and b. Once I know where f of a and where f of b is, then any point between them, so here's a value L. The conclusion of the intermediate value theorem says there must be a point where the function has that value. So if I draw a line, I can see that my function crosses my line at L somewhere between a and b. And that point, the value c that's between a and b, is what's guaranteed by the intermediate value theorem. It's useful to see why the hypotheses are required. I just want to show that if my L is not between f of b and f of a, then my function might cross it, or it might not. If I pick a value down here, there is a point where it crosses that's between a and b. On the other hand, at this other point, if I pick this larger value of L, the point where it crosses is not between a and b. This lower point illustrates the idea that sometimes the conclusion can be true even when the hypotheses are not satisfied. The hypotheses are simply conditions that do guarantee. It doesn't mean that there are other conditions that might also work. So now for a function that's not continuous. Here's a function that's not continuous on the interval from a to b. I have a value for my function at a, and I also have a value for my function at b. And because my function is not continuous, there are some of these values L that do lie between f of a and f of b, but that they never cross the function. So in order to guarantee that there's a value c where the function crosses a height L, the function has to be continuous for the intermediate value theorem to work. The second major named theorem is the extreme value theorem. The extreme value theorem is a theorem that guarantees the existence of global minima and maxima for the function. So what do I mean by that? A minimum is a function, it's a value of the function that is the lowest the function ever reaches. So what this is saying is my function is always above or equal to the minimum, and it's always less than or equal to the maximum. So here on the left I have a minimum, on the right I have a maximum. The extreme value theorem is saying that a function has a minimum and a maximum inside of a closed interval. All that's required for this to be true is that the function is continuous on the closed interval. If my function is continuous on a closed interval, it must have a minimum and it must have a maximum value on the interval. To illustrate this theorem, I've drawn a function that is continuous. I have an interval from a to b, and my function is in fact continuous from the value a to b. For my particular example, my function is increasing on the entire interval. And so my minimum value is at a, and my maximum value is at b. The extreme value theorem guaranteed that I could find those 2 points so that my function, f of x, is always between the highest point f of c big M and the lowest point f of c little m. This is seen by observing that my function stays inside of my box between a and b. It does not need to stay inside the box outside of the interval, just inside the interval. To illustrate another example, here's another function that is continuous between a and b. At a and at b, my function is continuous. If I look for a highest and lowest point, my extreme value theorem guarantees I can find them. I find a highest point in the middle, and this time my lowest point is at b. The extreme value theorem guaranteed I could find those 2 points, the minimum and the maximum point, and that once I found them, my function between a and b had to stay between the minimum and the maximum value. So what could go wrong if I am not continuous? Here's an example of a discontinuous function. It looks like there's a maximum value and a minimum value. My function stays between those 2 lines. If I call this point of discontinuity C, this highest point is not f of c, because my f of c is this actual point in between. In other words, my function does not actually reach a maximum value. It gets closer and closer through a limit, but it never actually reaches that maximum value. Similarly, I might have a vertical asymptote instead of ending at a point. We'll see the remaining theorems in the second part.